So now we're going to examine the different types of catalysts. Basically, you've got type 1, which we will call here heterogeneous catalysts. And we'll also call type 2, which is homogeneous catalysts. Now note, all catalysts are specific to a reaction. So you can't just go, oh, platinum is a catalyst, so it's a catalyst for everything. You can't just go, oh, you know, chlorophyll is a catalyst, so it's a catalyst for everything. It depends on the reaction. Some catalysts do work for multiple reactions, but it does need to be specific to that reaction. And they all work, you know, at a general level by reducing activation energy. Now, of course, we'll now be considering how that is done. So these are quite fancy words, but essentially heterogeneous catalysts, as far as you're concerned, is basically the catalyst is in a different state or phase to the reactants. So for example, the catalyst is nickel and the reactants are gases. So for example, nickel metal, so it's solid and the reactants are gases, or any sort of thing like that. And we might also note here, this is kind of borderline to HL, but basically transition metals are often heterogeneous catalysts. So a lot of transition metals, nickel, platinum, rubidium, palladium, etc., are often catalysts in the sense that they are solids and they are used as catalysts for reactions which are often gases, for example. And a homogeneous catalyst is basically a catalyst whose state or phase is the same as the reactants. So, you know, liquid with liquid, gas with gas, and so on. So, for example, acid in an esterification reaction. So you might remember for an esterification reaction, we had our alcohol, which is a liquid, plus our alkanoic acid, which is also a liquid, and it reacts to form your ester, which is often a liquid as well, plus water. But you might also recall that we had a catalyst. What was our catalyst here? Concentrated sulfuric acid, and that this was performed under reflux. You seem to have forgotten your organic chemistry. And this here is our catalyst. And note that this is, well, you know, it's in liquid/solution form, which is the same sort of phase. So this would be a homogeneous catalyst. So the catalysts are quite simple. You know, they're split into two types. One's basically called heterogeneous and one's called homogeneous. And you know these words from, you know, 2 terms ago at this point. Here in this context, we're basically saying, are they in a different state to the reactants or in the same state to the reactants? Does that make sense?
Yeah.
Now, sometimes you'll hear these referred to as, you know, type 1 and type 2. In the IB course, you know, they should be referring to that as homogeneous and heterogeneous catalysts. Now, both of these work to reduce their activation energy. We won't go into this in too much detail, but we will go into it in a little bit of detail. So your heterogeneous catalyst is basically your surface catalysts and are typically your transition metals. So typically is a solid, e.g. metal, and often a transition metal. Not always, but often it is. So common examples would be platinum, palladium, rubidium, nickel, etc. So you might recall that, for example, in an addition reaction of alkene with not a halogen, because that might not need one, but if you were doing, for example, an alkene with hydrogen, so do you remember what happens if you do a typical addition reaction of an alkene with hydrogen? What is the reaction? Gives you?
Well.
Yeah. So for example, ethene plus hydrogen. What's going to happen here?
Is this the hydro something reaction?
What's going to happen is that the double bond will be broken open.
Yeah. And it goes to the side.
Yes. So you will end up getting what?
Alkene.
Yeah, you get an alkene. Right? So this will just give you your ethane. And it's your alkane. And so that's basically just from organic chem. But what's relevant to you here is, of course, that you need a catalyst. And do you remember the catalyst for this?
No.
So the catalyst for this typically will be nickel or platinum, right? So let's just write nickel. And that, therefore, you can see, because ethene and hydrogen are both gases, and nickel being a solid, this would be acting essentially as a heterogeneous catalyst. All right?
Mm-hmm.
And you'll see these examples quite a lot, all right? So you've come across these before in these contexts in your organic chem. So this is an example of a heterogeneous catalyst in action. You've got, an alkene plus a hydrogen. Through the help of nickel, reacts to form alkane. Now, how does this nickel help? Well, this is where we won't go into it in too much detail, but essentially, a heterogeneous catalyst increases reaction rate by, well, all the, same thing applies to all catalysts by, reducing the activation energy of the reaction, as with all catalysts. And therefore, increasing the number of, successful collisions. Again, as with all catalysts. Now, where it is different is how it achieves this. And so essentially, it achieves it by providing a surface which is, if you like, conducive, basically helps to the reaction to occur. And this is where, we can go into a lot more detail, but it's kind of, outside the realm of HSL. So essentially, like a little bit of sort of here. So essentially, by the surface provided often basically orientates the reactants in a way that increases the probability of a successful collision by increasing the chances of essentially collision with favorable geometry. You might recall earlier we said for a successful collision, we require, or we need to consider, the energy level of the particles, as well as the geometry of the collision. And I mentioned, whether it's favorable or not. And I mentioned that these two aren't exactly mutually exclusive, but essentially, a heterogeneous catalyst mainly targets the geometry. The surface essentially, orientates the molecules in a certain way, which means that they're more likely to be hit in a way which will favor the reaction to occur.
Yeah.
So that's a bit technical. We can use some analogies to try and just kind of describe this. I don't really want to draw the sort of get into the energy levels of the surface and all that kind of thing. But essentially, it's a little bit like saying, let's say you want to study. A student wants to study. Now, if a student wants to study, they could, for example, all they really need is the student and the textbook, right? That is all you need, right? You need a student and whatever, your phone or like your textbook, your electronic, like your computer, whatever, right? Now, you could kind of study anywhere, but if you were to study, for example, in a noisy environment, so for example, next to a busy road with lots of people walking around and everything, versus, in a library, do you think you'll get the same amount of work done?
No.
No. So a catalyst is kind of like that. See, the reactants are kind of like your textbook and you, right? You need you to study and you need the textbook to study whatever subject you're doing. You can't not have it, otherwise you can't do it. But just because you have your reactant doesn't mean the ease with which they interact will be the same. If you're doing it in a noisy environment, then, sure, you're studying, but it's not very easy and you might not remember much. But if you do it in a library, then comparatively, or you would hope, you get to study, a lot kind of nicer, like a lot more effectively. Does that make sense?
Yeah.
So a catalyst, in the case of a heterogeneous catalyst, is a bit like, here's a library. So students who are in the library can study more effectively compared to, without a library, in your general situation, it's not as easy to study.
Yeah.
Now, it's a little, again, not the best example, but you could also imagine, for example, if you've got an open field and you've got, for example, a vehicle like a tank. Now, do you know where tanks are most strongest and where they're most vulnerable?
No.
Well, tanks, because they normally face an enemy, have the strongest armor at the front and the weakest armor at the back. If we ignore top and bottom, all right? So basically, if you've just got an open field and you've just got tanks running around everywhere, in all sorts of random directions, then, well, you may get lucky and, you know, hit them towards the back, or, you know, you may get unlucky and hit them towards the front, but there's no real kind of, because they're just randomly bouncing around, you know, in any sort of direction and velocity, there's no real sort of bias towards one direction or another. You know what I mean? You could also have a tank kind of running this way. Do you see what I mean? Like, there's no sort of bias towards with one's going, you know, whether you're likely to hit forward or backwards. Does that make sense?
Yeah.
However, let's say that you somehow then now create this battlefield where, for example, you create a one-way street. So essentially, you know, if you think of this as the sort of surface, and basically, okay, you've now, you know, got a traffic controller which says, okay, if you're a tank, you can only go, you know, it's a one-way street, at least, you know, until you get to the end. All right. So any tank that approaches here, you know, let's say they're forced to kind of enter head first. Well, that means your tank's going to enter like this. Does that make sense?
Yeah.
And if you imagine that all your other reactants are just bouncing here to attack, are they now likely to attack the front or the back?
The back.
Right. So it's not that the tank got weaker. It's always had this weak point. But now that you've essentially created this environment where the tanks are forced or sort of encouraged to face that way when they reach this area, that essentially increases the length of time that and the probability that their vulnerable side is exposed. Does that make sense?
Yeah.
And the same thing applies except with molecules on a molecular level. They're orientated in a certain way so that the angle of geometry of the collisions means that they're more likely to break the bonds, essentially.
Yeah.
Good. Does that make sense?
Mm-hmm.
So that's essentially how a heterogeneous catalyst works. So now our next question is, what about homogeneous catalysts? How will homogeneous catalysts work?
Would it increase the energy?
Well, they can't increase the energy because after all catalysts decrease the energy, and increase the energy is the job of a temperature, so not a catalyst. So now we'll need to think of how else can this be achieved. If a heterogeneous catalyst works by essentially targeting the geometry, then we will now consider how a homogeneous catalyst might work to do this.